In this video, we're going to talk about area as it pertains to the limit definition. So in our last video, we talked about chunking up the area under a curve and figuring out the lower sum and the upper sum. And we ended that video talking about, if I took the limit as n approaches infinity of both the lower and the upper, I actually get a value that is the same for both. And so that must be the area under a curve. And so here we have the definition of the limit of the lower and upper sum. So f is our function, and it's got to be continuous and non-negative on an interval from a to b inclusive. And we're going to take the limit as n approaches infinity. Remember that n represents the number of rectangles that we break it up into. So if we have an infinite amount, we should be able to get the area under a curve. And so we apply that to that same equation that we had before with the lowercase m and the uppercase m times delta x. Remember, that's b minus a over n. And so we're going to do that same work from the last video, but we're going to apply the limit. So that's going to include less work for us and a much better value for the area under a curve instead of just like, well, it's between this number and this number. And here we see the definition of the area of a region in the plane. So it essentially is describing what we've been working towards, but here's the formal definition, which still applies the limit as n approaches infinity, that same summation, the same delta x, and so forth. Okay, let's put it into practice. So let's say I have a function, x cubed, and I want to bound it by the x-axis, and x equals 0 and x equals 1. So I approach this first with this thing in purple here, my area equation in terms of the limit definition. And as a reminder, this c sub I is a plus I times delta x, and delta x is our b minus a over n, and b is 1 and a is 0. So this c sub I is for my right endpoints, and so my right endpoint here is 1 because it's to the right. So what I'm going to do now is figure out what this value and what this value is, and then plug it into this x cubed and figure out what my limit equation will be in terms of this summation. So I keep this first bit, the limit and the summation, the same, and I have f of this c value. So a is 0, and then I'm going to add I times whatever delta x is, and so b minus a is 1 minus 0. Or 1 over n. So I've got f of I times 1 over n times 1 over n, which is delta x. So I'm going to simplify that and see what I get. So if I plug in this I over n into my f of x, that's just going to cube I over n. And I have a 1 over n here, and so the denominator is actually n cubed times n, which is n to the fourth. So that's 1 over n to the fourth that I can pull out ahead of our summation. And then what I'm left with here is I cubed, which I have an equation for in terms of n. So I'm going to plug that in, figure out what I get, apply the limit to it, see if we can't find a number value for the area under this curve. And so next I substitute my equation in terms of n with this summation to n of I cubed, and that's this quantity. And to save some space, I did my algebra off screen. So I'm left with the limit as n approaches infinity of 1/4 plus 1 over 2n plus 1 over 4n squared. And if I apply this limit as n approaches infinity, all I'm left with is 1/4 plus 0, which is equal to 1/4, which is the area underneath this curve. So let's work through another example, and let's say our function is 4 minus x squared, and let's bound it by the x-axis, and x equals 1 and x equals 2. So the first few things I set up are my area equation, my value for c sub I, which is a plus I times delta x. Delta x is 2 minus 1 over n, since a and b are 1 and 2 respectively. So delta x is 1 over n, again. And a plus I times delta x is 1 plus I times 1 over n. So let's plug some stuff in, see what happens. So again, I bring down my limit and my summation symbol, and I plug in c into my function f of x. So I get 4 minus 1 plus I over n, which is my c value, and I square the c value, because that's x squared. And then I multiply by 1 over n, which is our delta x. So what I end up doing here is I FOIL this, and then I'm going to get a denominator of n squared. So I have all my terms FOILed out here, and then I'm just going to tack on a 1 over n. So that just makes this whole thing all over n cubed. And then I'm going to simplify the 4n squared minus n squared, which is 3n squared. And I'm going to break it up into 3n squared over n cubed, which puts a 1 over n on the outside here and leaves me a sum of 3 if I break each term up. And what I'm left with this negative 2i n over n cubed is 2 over n squared in the front, and the summation of just I. Because remember, I'm always trying to find summation in terms of just a number or in terms of I. And so this last bit here is negative I squared over n cubed, which leaves me with 1 over n cubed on the outside and the summation of I squared. And you probably already figured out that the next steps are to simplify each of these terms in terms of n, and then take the limit. So in doing that, I'm left with 3 minus 1 plus 1 over n minus 1/3 plus 1 over 2n plus 1 over 6n squared. I skipped a little bit of the algebra simplification from this step to this step, but you can fill it in on your own. And when I apply the limit as n approaches infinity, I'm left with 3 minus 1 plus 0 minus 1/3 plus 0 plus 0, which is 3 minus 1 minus 1/3, which, as a simple answer, is 5/3. So the area under this curve from the x-axis and from x equals 1 to 2 is 5/3. So let's do another example, but instead of bounding a function by the x-axis, we're actually going to choose the y-axis as a bound. So let's say I have f of y is equal to y squared, so that's going to produce this curve, and I want to bound it by the y-axis in between y equals 0 and 1 inclusive. So here again, I start with my area equation in terms of limit and summation, and I still have f of c sub I, but now I have delta y because I'm doing it in terms of y from f of y and not in terms of x. So the c subscript I is the same deal, a plus I times delta y though, obviously, work in terms of y. So a is 0 plus I times 1 over n because b minus a is 1 minus 0 over n, so that's delta y. Let's do what we have been doing and plug it in and apply the limit. So when I plug in this c value, which is I over n, I'm going to square it because that's what my function tells me to do. I'm going to multiply it by delta y, which is 1 over n. And I realize I can pull out, a 1 over n cubed because this makes n squared times n, so that's 1 over n cubed here, and I'm left with I squared. And I can substitute the summation of I squared in terms of n. Let's do that and simplify. So the summation of I squared is this, and I'm going to just FOIL out these terms and distribute the n to it and put them all over 6n cubed. So that's 2n cubed plus 3n squared plus n all over 6n cubed. I'm going to separate all of these terms here. So I have the limit as n approaches infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. And if you take the limit as n approaches infinity, you have 1/3 plus 0, which is 1/3. So the area under this curve, or actually above this curve, technically, bounded by the y-axis and between 0 and 1, is going to be 1/3. And our last example here has to do with the area that we've been working with, but instead of finding the exact value of the area under a curve, we're going to kind of go backwards and approximate area. So this is really good when you have a certain value for n, so a certain value of rectangles that you want to cut your equation up into. So let's work through this in terms of an example. So let's say I have this function, sine of x, f of x equals sine of x, and I want to bound it between the x-axis and between x equals 0 and x equals pi inclusive. So notice that the midpoint rule here, this is what we're using, called the midpoint rule. Didn't mention that before. With n equals 4, we're going to approximate the area under this curve. So instead of using that c value, we're actually going to use this value here. So x sub I plus x sub I minus 1 all over 2. Same delta x rule, so let's work this out. So given n equals 4, I can actually find my delta x to be in terms of a number and not n. So I get pi minus 0 over 4, so that's pi over 4. So that means between 0 and pi, and I have 4 subsections. each subsection is going to be chunked up in terms of pi over 4. So that width of that rectangle is going to be pi over 4. And so the next thing that I do is find my 4 values of c. So that's c sub I, c sub 2, c sub 3, and c sub 4. I have 4 because n equals 4. Not rocket science, but what I do is I'm going to add my first x and my second x value in that restriction. So I would add 0 plus pi over 4 divided by 2, I get pi over 8. Going to do the same thing for the next interval, so I do pi over 4 plus pi over 2 divided by 2, that's 3 pi over 8. And then the third interval is pi over 2 plus 3 pi over 4 divided by 2 is 5 pi over 8. And 3 pi over 4 plus pi over 2 is 7 pi over 8. So next I'm ready to throw it into this area equation. So know that it's the approximation, so there's no limit as n approaches infinity. We have a fixed n value. So I have the summation of f of this c value times delta x, which is the summation of sine of that c value times pi over 4. And what that looks like is that pi over 4 times sine of pi over 8, which comes from here, plus sine of 3 pi over 8, which comes from right here, plus sine of 5 pi over 8, which is from there, and sine of 7 pi over 8, which is right here. Throw that into my calculator in radian mode, and I get that approximation of the area under this curve with those bounds to be 2.052. And that's going to do it for this video. Thanks for watching.